In this video, we're going to take what we've learned so far about the first and second derivative tests and finding maximum and minimum values to find what we refer to as absolute maximum and minimum values. So when we talked about the first and second derivative tests, we found max and min values. Keep in mind we were finding relative max and min values. That means the highest or the lowest point in relation to the points around it. But that doesn't necessarily guarantee that the highest and lowest points we find are truly the highest and lowest points if you look at the entire graph of a function. They are highest and lowest in relation to the points around them. So you can think of them as being sort of the peak on a function, the valley on a function, but they may not represent the actual absolute highest and lowest values. So we're going to talk about how you would take what we've learned in those two sections, how we use those derivative tests, in order to find the truly highest and lowest points on a graph. So again, we can extend the concept of relative extreme values. In other words, the maximum or minimum on an interval in relation to the values around it, in order to find absolute extreme values. That is, the absolute highest and lowest values over a function's entire domain. Or, alternatively, the absolute highest and lowest points over an interval. Not necessarily the peak or the valley, but truly the highest point in a section of a graph. So just to show you what we're talking about with relative versus absolute maximum and minimum values, we used our derivative tests to find relative maximum and minimum values. In other words, anywhere where we would have a peak or a valley based on the shape of our graph, either the first derivative or the second derivative test could be used to determine those locations, and then those particular x values will be associated with the actual maximum and minimum values. So we know that those locations are going to occur anywhere we have a critical value. In other words, if we take the first derivative of our function, find the values of x that would make that derivative equal to 0, well, those particular values of x are associated with critical values. Those are the locations where we possibly can find one of these peaks or valleys. But notice on a graph like this, for instance, this would be the absolute lowest point. And notice, based on the fact that it's at the valley of that particular curve, if we want to call it that, this particular x value, this location, would be associated with a critical value. In other words, we could find this location just using the first or second derivative test. However, if you look at this entire graph, the absolute maximum, the absolute highest point, would be located over here. Now, in terms of the shape of the graph, we've got a valley, we've got a peak, we've got a valley, and then this point doesn't seem to be related shape-wise to these other 3 points that, again, we could find those locations using the first or second derivative test. But this would be the absolute maximum value over this range of x values on this particular graph. But again, notice this would not necessarily be associated with a critical value because we don't see the kind of behavior we see here. So using the first or second derivative test would not allow us to find this particular x value on this graph where we truly have the highest point on the graph. Well, if the first and second derivative tests aren't going to allow us to find this location where we truly have the highest point on the graph, how do we find it? Well, we're going to take the first and second derivative tests and we're going to add on a little bit to that. And that's going to allow us to find the absolute maximum and minimum values. So we're going to use the same strategies we've been using, but we're going to add on just a little bit in order to deal with this issue of what happens when our absolute max or min doesn't occur at one of these kinds of locations. What if it occurs somewhere like that or somewhere like that? Okay, so let's talk about what we call the maximum and minimum principle. So if we are looking for absolute extreme values, and we'll just focus on some interval from A to B, in other words, a particular range of x values, we want to find the truly highest value and lowest value on that particular interval. one of two things is going to happen with respect to our absolute extreme values. They must occur at one of two different locations. They're going to occur either at our critical values, in other words, those ones that we find from our first derivative, those locations where we potentially have a valley or a peak on the graph, or alternatively, they're going to occur at the end points of the interval. And that's what we see from this particular graph. So our lowest value would be associated with a critical value. We would find that particular minimum based on the fact that this location is represented as a critical value. It's a location where our derivative would have a value of 0. But the absolute maximum in this case is not associated with a critical value. The absolute maximum happens to occur at the end point of the interval that goes from x equals a to x equals b. So if we want the truly highest or lowest point on our graph, it's going to occur either at the location of a critical value or at one of the end points on the interval that we're checking. So that's going to lead us to what we refer to as the maximum and minimum principle. So suppose our function f of x is a continuous function. We know what that means now. Think intuitively, just no breaks, no holes. You could draw the graph without lifting your pencil. So suppose our function is a continuous function defined over an interval of x values that we're going to call the interval a to b. So this just means all the x values from a to b, including a and b. So to find the absolute maximum and minimum values on that interval, we have a 4-step process. So number 1, think first derivative test. Essentially, we're going to apply the first derivative test. Well, that always starts by finding the first derivative. So we want to start by finding f prime of x. Now we're going to use that derivative to find the critical values, specifically the critical values between a and b. We're only looking at this particular range of x values. So we're only interested in values between those two endpoints. So we want to find critical values based on our first derivative that occur between those two endpoints. So we're going to make a list of all of these values, and we're also going to add the values a and b, which again represent the endpoints of the interval we're checking. And then we're going to evaluate our function, f of x, the actual function, at each of the values in the list. So we're checking f of x at our critical values, and we're also checking f of x at a and at b. So the highest value that results from evaluating each of these x values plugged into our function represents the absolute maximum over our interval, and then the lowest value represents our absolute minimum. So essentially the idea is we're making a list of all the possible locations where we could have an absolute maximum and we could have an absolute minimum. In order to determine which ends up being our maximum, our minimum, or specifically the location for that, we plug it into the function and we just look for the highest and the lowest value. And so once we find the highest value, that represents our maximum. The associated x value is the location for the maximum. And then once we find the minimum, the lowest value, that's the value for the minimum, and then the associated x value tells us where that minimum is going to be located. So it's really just the first derivative test, using the first derivative, and then adding on just a little bit more, plugging into our function, looking at our y values, and then assessing the function from there. So let's try a couple of examples, finding our absolute maximum and minimum values. Okay, so for the first example, we want to find the absolute maximum and minimum values of the function f of x is equal to x to the 4th power minus 2x squared plus 5 over the interval from x equals -2 to x equals +2. So in other words, we're asking the question, if we were to graph this function and just look at the region of the graph between the x values of -2 and 2, what's the highest value, what's the lowest value on that interval, and where do those highest and lowest values occur? So in order to make the list of possible highest and lowest values between these two x values, we start with our critical values, which again we know those represent the locations where we might have a valley on our graph or a peak on our graph. So we need to find our first derivative. That's where we're always going to start. So take the derivative of our function. So that's going to be 4x cubed minus 4x, and we differentiate 5 and it goes to 0. Okay, now we know critical values occur wherever our first derivative is equal to 0. So we're going to take our first derivative, set it equal to 0. Now, as we've discussed, we can't move a term and divide out our variable. We can't eliminate the variable because that eliminates solutions to this equation. So instead, we factor this equation. So start with the greatest common factor. We're looking for things that these two terms have in common. So in this case, they have a 4 and an x in common, which leaves us with an x squared from our first term, and then -1 from our second term. Now what's left over factors as a difference of squares. So that's going to be 4x times x plus 1 times x minus 1. And so now that our function is fully factored, we can take each of these factors, set it equal to 0, and so we end up with critical values at -1, 0, and 1. So these represent 3 possible locations where we could find a maximum value or a minimum value. Now, in order to find the absolute maximum and minimum values over our interval, we need to determine what's the y value associated with each of these critical values, which one's highest, which one's lowest, but also we have to check the y values at our endpoints, because our endpoints also represent locations where we could peak or where we could hit the minimum value. So essentially we're going to check this list of values. We're going to check -2, our left-hand endpoint. We're going to check all 3 of our critical values, so -1, 0, and then 1. And then we're also going to check our right-hand endpoint at +2. By checking, again, that means we're going to take these possible locations for our max and min, plug them into our function, find the associated y value for each of these x values, and then we know the highest value represents our maximum, the lowest value represents our minimum, and then the associated x values represent the locations where we find that maximum and that minimum value. Now, this is a great time to use your graphing calculator as a time saver. So we're going to sub in each of these values, so f of -2, f of -1, f of 0, f of 1, and f of 2. And of course, we could do this evaluation by hand, which would mean taking this, subbing it in place of our variable in our function. But again, we can use the graphing calculator to save some time. So let's type in the function to our graphing calculator. Now be careful, you're not typing in the derivative, you're typing in the actual function. We want to know what the actual y values are associated with these x values if we were to graph this function. So x to the 4th minus 2x squared plus 5. And let's go look at our table. Okay, so there's the table. Now we're evaluating over the interval from -2 to 2, and we're looking at those endpoints at -2 and 2, and we're also looking at our critical values at -1, 0, and 1. So f of -2 based on our table is going to have a value of 13. F of -1 has a value of 4. F of 0 has a value of 5. F of 1 has a value of 4, and then f of 2 has a value of 13. So based on this, the lowest value we reach is going to be the value 4. But notice we reach that lowest value at 2 different x values. So the critical values -1 and 1 are associated with the minimum value, but they're both associated with that. So we would say that our absolute minimum is the value 4, but it occurs at two different x locations. It occurs at both x equals -1 and x equals +1. So because that is truly the lowest value and it occurs at two different locations, we want to notate that. We want to make a note of saying this is the minimum value, but it happens to be reached at two different locations. So two locations in this case represent that value of that absolute minimum. Now the highest value we reach is going to be 13, and notice it occurs at both of our endpoints. So our absolute maximum value is going to be the value 13, and it occurs at x equals -2, our left-hand endpoint, and x equals +2, which is our right-hand endpoint. So it's possible we can run into a situation like this where there's not a single lowest or a single highest point. We have maybe more than one value associated with the lowest possible y value, and so we make a note that this lowest value and this highest value occur at different locations. Now let's try another example. Okay, so we want to find the absolute maximum and minimum values of this function. F of x is equal to x cubed minus 3x plus 2. We want to look at two different intervals. So first, we're going to look at the interval from -2 to 3/2. And second, we're going to look at the interval from -3 to -3/2. So we have to keep in mind when we talk about absolute maximum and minimum, either we can talk about it from the standpoint of the whole domain, in other words, truly the highest and lowest points, or with respect to an interval. And as we look at different intervals may have different highest and lowest points from one another because we're looking at different portions of the graph. So let me get out of our graph here so we're not looking at any of those numbers, and then let's get started. Now, where we start is going to be the same. Since we're looking at the same function for both of these intervals, the critical values are going to be the same, and of course the critical values come from our first derivative. So start by taking the first derivative. So f prime of x is going to be 3x squared minus 3. We know our critical values occur where our first derivative is equal to 0. Now, either we can factor here, or notice because we only have one instance of x, we can also isolate that by moving things to the right-hand side of the equation. So that's probably going to be a better option here. So I'm going to add my 3, move it over. So that gives me 3x squared is equal to 3. If I divide by 3, I have x squared is equal to 1. And so that means x is going to be positive or -1. Don't forget, when you take the square root in an equation, you have to have a plus or minus in order to indicate that two different values could be squared and result in an output of +1. So these are going to be the two critical values for this particular function. These are the possible locations of valleys and peaks on this particular function's graph. Now, what about our absolute max and min over our particular intervals? Well, our first interval is going to go from -2 to 3/2. So in order to check for the lowest and highest points over this interval, we need to check our end points, so -2 and 3/2. And then we also need to check any critical values that occur on this interval. So -1 occurs in this interval. 3/2 is the same thing as 1.5. So notice that +1 will also be contained in this interval. So we need to check all of our critical values as well as both of our endpoints in this case. So we're going to take each of these 4 possible locations for our max and min, sub them into our function, and then find the lowest and find the highest values. So we want f of -2, f of -1, f of +1, and f of 3/2. Okay, so let me bring that function back up. And again, let's use the graphing calculator to save ourselves a little bit of time. So y equals, let's clear this out, x cubed minus 3x plus 2. Now, if I bring up the table, I'm going to see negative 2, negative 1, and 1 represented as x values, but I'm not going to see 3 halves because I know my table is set up to just transition by integer values along x. So instead of just looking at the table as is, I'm going to go and change the settings real quick. So second in window, table settings, I'm going to set my independent variable to ask. That way we can just type in the x values we want and just check those values. So we want to check negative 2 first. So x equals negative 2 is associated with a y value of 0. X equals negative 1 is associated with a y value of 4. X equals positive 1 is associated with a y value of 0. And x equals 3 halves is associated with 0.875. Well, what does that mean? Well, because we have a decimal value here, that means it's probably going to be a better option to evaluate this particular one using the actual home row there in the calculator. So I'm going to get out of my graph, and I want to actually evaluate what happens when I plug in 3 halves, but I want to evaluate it here just typing it in. So minus 3 times 3 halves plus 2. Let's double check that I typed everything correctly. 3 halves cubed minus 3 times 3 halves plus 2. Now notice we get the same value, but here we can use math and arrow frac to convert that to a fraction. And that's going to give us the fractional value 7/8. So in this case, the lowest value we reach is the value 0. And again, it happens to occur at 2 different locations. It occurs at x equals negative 2 and at x equals 1. And in this case, the highest value we reach is 4, and it occurs uniquely at this single x value, x equals negative 1, which was one of our critical values. So our absolute maximum is going to be 4, and it's located at x equals negative 1. And our absolute minimum value is 0, and it's located at 2 different locations, x equals negative 2 and x equals positive 1. Now, what happens when we change the interval? So here we were looking all the way from negative 2 to 3 halves, which is on the other side of 0. For the next interval, we're just looking over a range of negative values, so negative 3 to negative 3 halves. Now, we don't have to take the derivative again. The derivative is based on our original function, and we're still looking at the same function, so it still has the same critical values. So what we now have to decide is what values will we check based on the fact that this is going to be the interval that we're looking at. Well, we know we always have to check our endpoints. So negative 3 is our left-hand endpoint. And then we also want to check any critical values that occur within this particular interval. So our critical values are positive 1 and negative 1. Well, positive 1 is definitely not within this interval because this interval only contains negative values. What about negative 1? Well, in this case, negative 1 is going to be outside the interval. Negative 3 halves is negative 1 1/2. So if you were to think in terms of a number line, if this is negative 3 halves, negative 1 is more in the positive direction than that. So it is not within this interval. So that means in this case, we're only going to check our endpoints. 1 is going to represent the location of our maximum. 1 is going to represent the location of our minimum. And again, the reason we only check the endpoints is because this particular interval doesn't actually contain either of our critical values. These are the only locations for critical values. They're not within this interval. So that means our max and min have to occur at our endpoints. So now we just need to check those endpoints. So f of negative 3 and then f of negative 3 halves. So again, we can use the graphing feature if we want. So I'm going to go back into the table. What happens if I sub in negative 3? Well, that's going to give me negative 16. And then we'll try negative 3 halves. We'll see what happens. So negative 3 halves. And again, we get a fractional value. So let's go back out and let's just type that one in by hand. So negative 3 halves, and we're raising that to the third power, minus 3 times negative 3 halves, plus 2. Okay, and again, we get the same value, but now we can convert it to a fraction. And so that's going to give us a value of 25 over 8. And as a decimal, 3.125. Well, clearly this is a positive number and this is a negative number, so this has to be the lowest value and this has to be the highest value. So in this case, our absolute maximum is the value 25 over 8, otherwise known as 3.125, and it occurs at x is equal to negative 3 halves, in other words, the right-hand endpoint of our graph, and the absolute minimum is negative 16, and it occurs at the left-hand endpoint, x equals negative 3. So depending on the interval we're looking at, depending on the function we're looking at, sometimes our absolute max and min occur at our endpoints. Sometimes they occur at critical values. It just depends on the function. It depends on if we're looking at an interval containing our critical values or not. It's going to vary just depending on the situation that we're looking at. So let's wrap up with a couple of examples. The focus is on how we use this idea of maximization, minimization, particularly in the context of a real problem. So if we have a function representing a real situation, potentially we want to find that function's maximum or its minimum because that may represent something in the context of the actual problem that we're looking at. We can use this same strategy, this idea of finding the absolute maximum and minimum, in the context of a real problem as long as we have a function representing that problem. Okay, so let me clear out my calculator. Let's clear out the graph. That way if we need it, we can type it in. Okay, so the percentage of unemployed workers in service occupations can be approximated by the following function. P of x is equal to negative 0.039 x cubed plus 0.594 x squared minus 1.967 x plus 7.555. So x represents the number of years that have elapsed since 2003. So according to this model, we want to know in which year during the period from 2003 to 2013 was this percentage at its maximum? When did it reach its maximum? That's what we want to know. Okay, so first thing we need to do is evaluate our derivative. Let's start there. Now this function looks a little bit messy, but the only thing messy really is the coefficients. And keep in mind, otherwise we're just using the power rule. It just happens that we're using the power rule with coefficients that aren't especially pretty. So I'm going to bring down my 3, and I'm just going to do that multiplication in the calculator. So negative 0.039, and we're multiplying that by the exponent we brought down, which was 3. So negative 0.117, and then decrease the exponent to a 2, plus, bring down your 2, multiply, so 0.594 multiplied by 2, 1.188, decrease the exponent, so that just becomes an x. And then for the last term, we know this one goes to 0, but for the last term, bring down the 1, nothing changes, and the x just goes away. So minus 1.967. Okay, so we have to set that equal to 0. So negative 0.117 x squared plus 1.188 x minus 1.967 is equal to 0. And whatever x values satisfy that equation, those are going to represent our critical values. Now, this would need to be factored, or we would have to use some equivalent strategy to factoring in order to solve for x. Because our coefficients are not particularly nice numbers here, factoring is not a good option. So if we were going to solve this equation algebraically, we use what we call the quadratic formula. The quadratic formula will allow us to solve for x regardless of what our coefficients, what our constant values look like. But here, because we've got the graphing calculator, we can also use the graphing calculator to help us solve this particular more complicated equation. So we want to type in the expression representing the equation we're solving. So I'm not going to type in my original function. I want to type in the derivative, what I've set equal to 0. So negative 0.117 x squared plus 1.188 x minus 1.967. Okay, and I want to graph this. So that's what it looks like. I'm going to zoom back to Zoom Standard. Zoom Standard. There we go. Okay, so we're trying to determine where this function is equal to 0. Well, what that means is where is the associated y coordinate equal to 0? What x values have an associated y coordinate of 0? Well, we have a name for points that behave that way. We call those x-intercepts. And if you look at the graph of this function, it looks like it crosses the x-axis 2 times. It looks like we have 2 x-intercepts. So wherever those intercepts occur, those represent the x values that solve this equation. So how can we determine where those x-intercepts occur? What if they don't occur on an actual integer value? What if they occur between the tick marks? How do we determine where those locations are? Well, our calculator will do this for us. We don't have to estimate. So we're going to use the calc option, which is right above trace in blue. So I'm going to hit second and trace, and it's going to take me into the calculate menu. This will set up all the different things that the graphing calculator can calculate for you in relation to the function you typed in. So what we want here is option 2, 0. 0 is another term for x-intercept. So this particular calculate option is going to allow us to find the locations of our x-intercepts, find the values for those x-intercepts. So I'm going to highlight 0 and I'm going to press enter. And you'll notice down at the bottom of the screen it now says left bound. Essentially what we're going to do is we're going to set the locations of boundaries, one to the left of the intercept we're looking for and one to the right of the intercept. So our first intercept, it looks like it occurs maybe somewhere around x equals 2. So we want to set a boundary to the left of that, and we want to set a boundary to the right of that so that our calculator knows we want to check within this range, find intercepts just within this range. Now the cursor, which is flashing, is going to give us the location where we set our boundary. So where it currently is located is already to the left of our intercept. So I'm going to just leave it where it is, and I'm going to press enter. And it's going to set a boundary right there where I pressed enter. Now look down at the bottom again, it says right bound. Now we need to do the same thing, but we need to move over to a location that is to the right of our intercept. So I'm going to use the right arrow to move along the graph until I get to somewhere that is definitely to the right of my intercept, but not all the way over past the next intercept. So I'm at a location that's to the right of my intercept that I'm looking for, the one that looks like it's about at x equals 2. And so I'm going to hit enter again, and it sets a right-hand boundary. Now it just says guess. That just means, do you want me to guess where it is? Okay, so we're going to hit enter one more time, and it's going to give you the location of your 0. So in this case, it's not exactly 2, but it's somewhere close to 2. And so we're just going to round. In this case, it's going to be approximately 2.083. That'll work. So that is going to be, roughly speaking, one of the x values that solves this equation where we set our derivative equal to 0. In other words, this is the location, roughly speaking, of one of our critical values for our function where we could have a maximum or could have a minimum. Now we need to determine the location of the other intercept, the other x value that solves this equation. So I'm going to go back into the calculate menu. I'm going to click on 0 again. And now we want to do the same thing, but we want to do it for the next intercept. So I'm going to move over, set a boundary that's to the left of my intercept. It just needs to be to the left, but not to the left of the intercept we already checked. And I'm going to hit enter, and notice it sets that boundary. Now I need to set my boundary to the right. So again, arrow over until you get to the right-hand side of your intercept and hit enter again. And notice we've set bounds and the intercept is between them. So now I'm going to press enter one more time, and it's going to give me the location of that other value. And so if we were to round that, it's really close to 8, but about 8.071. So 8.071. Okay. So what about the maximum and minimum? What do we do now? Okay. Well, remember, with absolute maximum and minimum, we need to check two different things with respect to the potential locations for a maximum and a minimum value. We need to check the endpoints of our interval, and we also need to check the critical values. The maximum and the minimum are going to occur at either a critical value or at one of the endpoints of our interval. So these are our critical values. Our interval that we're checking is represented by this. Now remember, x is the number of years since 2003, and we're checking the range from 2003 to 2013. So we're not checking x equals 2003 and x equals 2013. We need to determine what these values represent in terms of x based on how x is defined. So for 2003, if we're thinking of x as the number of years that has elapsed since 2003, well, 2003 is going to be x equals 0. If we're looking at 2003, then the number of years that have elapsed since 2003, well, no years. And then the end value, 2013, that's going to be the number of years that have elapsed since 2003. So in this case, that would be 10 years from 2003. So we need to check our endpoints, and we need to check our critical values. We're going to substitute them into our function, and we want to determine where do we hit our maximum. It's either going to be at an endpoint or it's going to be at the location of a critical value. So let's use the graphing calculator again to help us out. Now we need to type in the actual function, because remember, we're checking these values within the original function. Where do we hit the highest value? Where do we hit the lowest value? Now as you type this, be really careful. This is kind of a mess to type, so just make sure you check your work as you go. Okay, minus 1.967x plus 7.555. Okay, and I'm going to arrow back over, tab back over, verify that I've typed what I intended, double check each of your terms, double check all your signs, double check your exponents. Okay, that looks good. Okay, so now I'm going to go into my table. Now we need to check values at 0, 10, and then our two critical values. Okay, so at x equals 0, and notice you already have some things in there. It's difficult to clear them out, so you can just type over them. That's perfectly fine. So at x equals 0, we have an associated y value of 7.555. So P of 0, sorry, P, not F. P of 0 is 7.555. Now that makes sense. If we sub in 0 here, notice these three terms go to 0, and we're just left with the value at the end. Okay, let's check the next critical value. So P of 2.083, our critical value. So 2.083, associated y value of 5.6826, 5.6826. Okay, and then P of our next critical value, 8.071. So 8.071. That's associated with a value of 9.8687. 9.8687. And then finally, check our further out endpoint at x equals 10. and we have an associated value of 8.285. So clearly, based on this, the maximum we reach is associated with the x value 8.071. Okay, well, how does that apply to the question we asked? The question we asked is, in which year during the period that we checked was the percentage, in this case the percentage of unemployed workers, at its maximum? Okay, well, this is the maximum value we reach, okay, and this is the associated x value. Remember what our x value represents, though. It represents the number of years that have elapsed since 2003. So this is roughly 8. It's a little bit more than 8 years, but if we're talking about just being inside of a year, it's within the same year that we reach after 8 years. So in other words, we reach our maximum 8 years after 2003. So the actual year in question is going to be 2003 plus this approximate 8 number of years. And so that is going to be the year 2011. So based on our function, the year where unemployment reached its maximum percentage is going to be the year 2011. Okay, let's try another example. Slightly different. Okay, so an electronics store determines that its weekly profit in dollars from the production and sale of X amplifiers, so X represents the number of amplifiers made and sold, is given by the function P of X is equal to 1500 divided by the quantity X squared minus 6X plus 1. We want to find the number of amplifiers for which weekly profit is at a maximum, and then find the associated maximum weekly profit. Okay, so P of X, our profit, that's going to be in dollars, and X is the number of amplifiers that we've made and sold. Okay, so we're looking for the maximum here. Where does it occur? What X value is it associated with? And then what's the associated maximum profit? Okay, so we need to find our derivative. That's where we're starting. Now with this particular function, either you can find the derivative using the quotient rule, that's an option, or another option is, we've talked about what happens when you have something in the denominator. If something is in the denominator, you can take it out of the denominator and rewrite it with a negative exponent. So that's going to be another option, and it may be a little bit faster here. So I'm going to take it out of the denominator by writing that expression in the denominator with an exponent of -1. So this expression and this expression, they are logically equivalent. So here I need to use the chain rule to take the derivative. So in this case, we're going to bring down our exponent, decrease the exponent by 1, leave the inside function alone, and then multiply by the derivative of the inside function. So our derivative is going to be 1500 times -1. So negative 1500 times x squared minus 6x plus 1. We decrease our exponent to -2. And then we're going to multiply by the derivative of the inside function, which is going to be 2x minus 6. Okay, let's clean this up a little bit. So we don't like to leave things with negative exponents. That's a good place to start. Everything else, the negative exponent does not apply to, so that will stay in the numerator when this moves to the denominator. So in our numerator, we have negative 1500 times 2x minus 6, and in the denominator, we take our expression x squared minus 6x plus 1, and that becomes a positive exponent in our denominator. So the only other thing we can do is maybe then distribute that negative 1500. So that's going to be negative 3000x, and then 1500 times 6, or negative 1500 times negative 6. Negative 1500 times negative 6 is going to be 9,000. And notice again, it's going to be positive because of that double negative. So plus 9,000 divided by our denominator. Okay, so there is our derivative. Now we need to find the critical values based on this derivative. Now, because this derivative has a numerator and a denominator, we actually have two possible situations where we might have a critical value. Critical values are associated with locations where the derivative is 0, but they're also associated with locations where the derivative is undefined. So in this case, if our numerator is 0, that means this whole expression is 0, which means the derivative has a value of 0. So any x value that makes the numerator 0 is associated with a critical value. Now, because this particular derivative has a denominator, if the denominator is 0, then that also means it's undefined, which means we have another critical value. So if there's an x value that makes the denominator 0, that also represents a critical value. So we need to split this up, and we need to look at our numerator and our denominator independently. So negative 3000x plus 9000 is equal to 0. Okay, so I want to solve for x, subtract the 9000. So negative 3000x is equal to negative 9000. And so x is equal to 3. Okay. What about our denominator? Well, we have an exponent applied to this expression, but think about this for a minute. If the denominator is 0, well, we had to take something and square it and get 0. The only thing we can square to get a 0 is going to be 0 itself. So if the whole denominator is 0, that means the expression in parentheses had to be 0. So x squared minus 6x plus 1 is equal to 0. What would make that 0? Well, ideally, I would try by factoring if I can. So I'm looking for numbers that multiply to give positive 1, that also add to give negative 6. And there aren't any numbers that do that. So factoring is not going to be a good option here. So just like the equation above, either we would use the quadratic formula to find the values of x, or just like we did here, we could graph it, and we could use some of the tools that our graphing calculator has available to us. So let's try that instead. It's a little bit of a time saver. So I'm going to type in that function that I have set equal to 0. So x squared minus 6x plus 1. And I'm going to look for x values associated with 0. So let's look at the graph. Okay. So in this case, we have two locations where this function could be 0. Okay? Oh, there's a mistake. There's a mistake here. Okay, let's go back up to the very top. Apologies. My printer cut something off. This should be a 10. Let's fix that. My apologies. Okay, so what does this change? This changes a couple of different things. Okay, so that's going to be a 10. 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 I've had some issues with my printer. Apologies for that. So that's going to be a 10 as well. Okay, so let's go back and fix this. Graphing wise, there's not too much to fix. Okay, so I just need to change that 1 into a 10. Apologies, I need to double check my printing apparently. So let's go back into the graph now. Okay, this looks how I expected it to look. What I want you to notice about this graph, notice it does not cross our x-axis. So if we're looking for x values that give us an associated y value of 0, well, this graph is all the way above the x-axis, which means it's never going to cross the x-axis. We're not going to have any x values that give us an associated y value of 0. So that means this particular equation can't be solved. There are no x values that make this true. So no associated critical values. Critical values would be the x values that make this equation true. I'm just going to put CV, no associated critical values. So that means this function only has a critical value at x equals 3. Okay, so that's going to be a number we have to check in terms of finding our maximum. Here's the problem though. With this particular problem, we haven't been given an interval to check. We haven't been given endpoints to check as well, because remember, we may have endpoints representing the location of a maximum or a minimum value for our function as well. So if we haven't been given endpoints, well, what are our endpoints? So we're looking in terms of the x values, what x values would represent endpoints. Now, x values here represent how many items we make and sell. Well, the smallest number of items that we can make and sell, that's going to be 0, right? So we can't make a negative number of items, but we can make 0 items. So if we want to set up an interval to check, the lowest value we could possibly have would be a value of 0, just based on the fact that we're in a real world situation. You can't manufacture and sell 0 or fewer than 0 items. Now, assuming we have unlimited resources, we could make and sell as many as we want. So technically speaking, the other endpoint would be positive infinity. We don't actually have a cutoff here unless we're told that we do otherwise. Now, we can't substitute in infinity here. We can substitute in 0, and then we can also check 3. So let's look at P of 0, and let's look at P of 3. And then we also want to look at the graph so that we can understand a little bit better about what's happening with this function. Where might we find a maximum? Where might we find something like that? So P of 0, well, let's type in our function so that we can evaluate it. Okay, so we have 1500 divided by, in parentheses, x squared minus 6x plus, not 1, but plus 10. There we go. Okay, so let's go back into the table. Now, we already have 0 typed in. 0 is associated with a y value of 150. So P of 0 is going to be 150, okay? P of 3, what happens if we enter in a 3? Well, P of 3 is going to be 1500. But what if we made more? So if we made and sold more, might we have a higher value of profit than 1500? Well, let's look at the graph and let's see if we can tell that from the graph. So I'm going to zoom back to Zoom Standard. Okay, so that's Zoom Standard. Let's zoom out just a little bit because we're obviously not getting the whole picture. So there's our graph. It looks like maybe there's a gap in the middle, but maybe there's not. How can we tell? Well, if you continue to zoom, you'll see a little bit more of the graph, okay? Still a little bit misleading, still can't really tell what's going on there in the middle. Now, we only really care about the portion of the graph where x is greater than or equal to 0, because remember, we can't manufacture a negative number of items. So the left-hand side of this graph to the left of the y-axis doesn't really mean anything in the context of our problem. Now, if we're just looking at the right-hand side, it looks like it starts out really high and then it just slopes downward from there. So the peak is going to be somewhere over there close to x equals 0. Well, we know there at x equals 0, we definitely don't hit the maximum. We think it might be at 3, since P of 3 gives us 1500, and that appears to be the maximum. Here's how we can use another feature to help us figure this out. I want to look at the table. But I want to set the table back to where it normally is, where the independent variable is on auto. I'm going to go back into the table. Now we just want to compare the values, and this is going to give us a sense of what the picture really looks like, even though we can't really see the picture as well from the actual graph. So again, we would start at x equals 0, because that's the lowest number of items we can make and sell. And again, there's 150. Well, if we increase by 1 item, we have a profit of 300. Increase to 2 items, we have a profit of 750, and then increase to 3 items, we have a profit of 1500. Now, as we continue on from there, notice the amount of profit continues to drop. Well, another question might be, okay, 1500 looks to be the highest number in this list, but how do we know the maximum doesn't hit somewhere between maybe 2 and 3, or between 3 and 4? Well, again, we have to think about what x means. X is a number of items made and sold. So if we're talking about a fractional x value here, that's like making and selling half of an amplifier, something like that. We can't make and sell half of an item. So So for this particular function, based on its context, based on what it really means, only whole number x values actually make sense in this case. So we don't have to worry about 2.5 or 3.5, something like that, because those kind of numbers don't mean anything in this context. So based on our limited x values that actually apply in this situation, x equals 3 is definitely going to be where we have the highest associated y value, in this case the highest associated profit. And so that answers our question. So in this case, our highest value occurred at our critical point of 3. Now what does that represent? Again, that represents the number of amplifiers. So the number of amplifiers where our profit is at a maximum is going to be 3. So x equals 3 amplifiers. That's going to be where we have the highest profit. So making and selling 3. And then the maximum profit, we subbed in 3 to our profit function, and we found an associated value of 1,500. So P of 3 equals 1,500. Well, that's going to be $1,500. That is our maximum profit. Making less than that, we don't make as much profit. If we make more than that, then our profit starts to decline from there. So these two examples hopefully give you a sense of how you could use this idea of maximization, minimization, using that first derivative test, the idea behind it, finding the critical values, and then extending it, checking endpoints on an interval, noting that an endpoint could also represent the location for a maximum or a minimum value. So we're going to spend more time looking at application problems. The idea is we don't want to use these particular concepts out of context. The idea is how can we actually use this to solve real-world problems. So we'll look at some more examples solving these kinds of applied problems. Sometimes we're given a function, sometimes we have to write our own function, and then find our max and min using the strategies that we've looked at in this section.